Hey everybody, Dr. White here with a little supplement to section 2.1. We're going to take a look at actually simulating what happens when you try a random variable a lot of times. So look, we're signed into R here. I have cleared my global environment by pressing the little broom, and I've also closed any R scripts that I don't need to be looking at right now. I head to .. /com. And in Dr. White stuff, Math 331, need to look into scripts, and you see a Chapter 2, Section 1 script, which I open up and say File Save As, .. back to my home directory, and double-click my notes and save into there. And I've already done that in a previous version before, so I have to say, yes, I want to replace. Alrighty, and by the way, I'm looking over into the common folder here. I'm going to go ahead and look back home. Now, let's see what we got. Going to load up a little package today that does graphs. So library ggplot2, command enter, run that. And want to imagine a random experiment where it's just that you roll a fair die. So there's 6 possible outcomes, 1, 2, 3, 4, 5, and 6. I want to associate a number with each of these outcomes, construct a random variable. Let's say you win $2 if the die lands 1. You lose $3 if it lands 2, 3, 4, or 5, and you win $15 if it lands 6. So I've assigned a number to each face of the die, got myself a random variable. Now I can think of the sample space of the random variable. The possible values for it are 2, -3, and 15. And what I'm doing with this command on line 14 is binding that little vector of possible values to the name x. When I run it, I get the name value pair. X is that little vector in my global environment. In the same way, I'm going to bind the name f of x to the probability for getting each of those possible values. Now, there's only a 1 in 6 chance of getting a 2 because there's only one way to win $2. But there's a 4 in 6 chance of getting a -3 because there were 4 sides you could land on to lose $3. And a 1 in 6 chance of getting the 15. So f of x really stands for the values in the probability mass function. Here it is in the global environment. All right, now we're actually going to try the random experiment and do the random variable along with it. So the way you can do that easily is with the sample function in R. What you do is you feed it as its first argument the vector that you want to sample a value from. You want to say how many values you want to sample from that vector. I want just 1, size is 1. Lastly, you got to say what's the chance of getting each of the values in the vector. That's called the prob parameter, and you set that equal to the f of x. So this is like trying out the random variable once. I'm going to try it right now. Got a -3. I'm going to try it again. Go down to console, up arrow, run that command again, and this time I won $2. Great. You can also simulate playing the game more than once, but you got to be careful. One thing you got to do is you got to set the size to be the number of times you want to play the game. Number of times you want to roll the die, and win or lose something. The other thing is you got to say replace is true. By default, replace is false in this function. And when it pulls a value out of the vector, it won't put it back in when you take another sample. And that's totally not what should happen here, because when you roll the die, you get a chance to get each side again, even if you've gotten it before. So we need to say replace is true, and then we'll really have the same chance of getting the 2, the -3, and the 15 each time. So let's give it a try. And we get, in this case, I lost $3 quite a bit at the time. So what I want to get a sense of is what happens when we try it a few times versus many, many times. Why don't I set times to be 30? Let's play the dice game 30 times. There's times is 30 in my global environment. Okay, next thing I'm going to do is bind the name winnings to the result of sampling 30 times. Size is times here. And I'm playing that game, so I'm setting up prob as f of x and replace as true. Let's give it a try. So winnings is a little numerical vector of length 30 here, and for me it started off losing $3 twice and then winning $2. You can make a table of what happened for you. On line 26 here, table of winnings. So let me run that, Command Enter. So I guess I lost $3 18 times, I won $2 4 times, and I won $15 8 times. You can make a table of proportions off of that table. And it just divides each of the accounts by 30, giving you the proportions that you see down here. Now, finally, you can make a bar graph. What I'm going to do is make that proportions table, just call it tab for short here. And then I'm going to make a data frame out of the table. You can ignore the code if you haven't had Computer Science 1 and just like run it. And got to run the tab line on line 30. Yeah. And now I can run the line that constructs df. And let's take a look at df by just going up and clicking on it. And so you can see there that it's saying that 60% of the time I lost $3, 13% of the time I won $2, and so on. And lastly, I can make a plot of those frequencies. And that's this ggplot command that goes from line 35 down to line 37. There it is. And I'm going to remove my face now so you can see the whole thing. And so each of these heights is like it was in the table, okay? 0.6, here we go. And over a 2, there should be a 0.133. Yeah, that looks about right. And over the 15, it should be about 0.266 high, and that looks about right. So that's what happened when I tried it 30 times. But remember the law of large numbers? What if I tried it a whole lot of times? Like, how about 30,000 times? What I'm going to do is just run that whole block of code here all the way down to the graph. And it all happens pretty fast. And I look up in the console, and here's my table of how it came out to me in my 30,000 tries. And you can see about 20,000 times I lost $3, but I often won $2 or $15. And here are the proportions of times that happened to me. And look at it, they're really close to the probabilities for getting the results. 2/3 was the chance of losing $3. 2/3 is 0.6666 repeating. This proportion was really close to that. Same for the other two proportions of times I got those values for the random variable. They're really close to the probability of getting the random variable. That is the law of large numbers that motivates that frequentist definition of probability. And these heights here in this graph are going to be almost indistinguishable from the heights that make up a bar graph for the probability mass function for this random variable. If I could have done it infinitely many times instead of just 30,000 times, then these heights would have matched up perfectly. Something I've just meaning to say and haven't said yet. When you do random stuff, every time you run the random stuff type of command in R, you get different random looking results. Sometimes you don't want that to happen because sometimes you want to be able to like report on and discuss and talk about random stuff that you got. So you can stabilize your random results by setting a seed. Look at line 42 here. Set.seed, and then what you do is you just put in an integer that you like, okay? And it starts R off at a certain place in its computations. And then it goes and does its random stuff. So let's give this a try. Call one, run. Now notice the 10 results we got for playing the game. Let's take a little look at them. And then I want you to With the same stuff selected, press run again. So you're running those same 2 commands again. You're starting yourself off back at the 40-40 place and doing your random stuff. And look at that. It was the same random looking stuff. No matter how many times you repeat those commands, you will get the same random looking stuff. Now, if you set the seed to something different, like down here in line 47-48, set the seed 34-25, and run that same sample command, you'll get different random stuff. You can see a little difference, see, between what you got now and what you got last time. But every time you run that same 2 lines, you will get the same random stuff. So setting seed can help you talk about values that you get, and in a report where if you give other people your code, they can get the same results that you got because they start from the same seed that you have set. Alrighty, that's a little illustration of the law of large numbers and how they can make your actual results in trying a random variable a lot of times approximate better and better the theoretical probability mass function for the random variable. That's all for now.